how a program can be assembled. And we said that you needed two tables. We said that you needed two tables. The operation code table, which has got all of the operation codes, which can be translated to machine language. And then the symbol table. You remember we said that usually when you are given a program, you are not given addresses. The instructions don't have addresses. Yet you need those addresses in order to assemble a program. That's why we said that normally a program is assembled using two passes. That the program is assembled using two passes. During pass one, the operation code table is checked to find out whether the written instructions are valid. So it is like debugging the program. It is like debugging the program where you examine the code to find out whether whatever you have written exists, whether what you have written is valid. Okay, so that during pass one, the operation code table is checked to validate the operation codes, and then again during pass one, that's when the symbol table is also generated. Okay, then in pass two, you use the two tables, the operation code table and the symbol table, which has got the addresses of the symbols, and then you translate the instructions into machine language. So I think we stopped around there, where we said that in pass one, the labels are entered into the symbol table as they are encountered. Then in the second pass, you use the symbol table and the operation code table to translate the assembler language instructions into machine language. Okay. Now, you remember we said that the main function of the assembler is to generate object code and a program listing. We said that it generates the object, it translates the assembler language instructions to machine language. And then it also generates what we call the program listing. Now I said that the program listing, these are the instructions which we need to load, which will be needed by the loader to load the program in memory. So the the machine language instructions which have been generated and the program listing, they make up what we call the object code or the object program. So it is the object program which is loaded in memory. It is the object program which is loaded in memory. Now, remember we are saying that the object program consists of the machine language instructions and then the information which will be needed by the loader to load this program in memory. Now, how does the object program look like? The object program has got three types of records. There is what we call the header record. Okay, so the header record contains the name of the program because that will be needed. You remember memory contains a lot of stuff. So if a program is going to be loaded in memory, perhaps there are other programs already loaded in memory. So this program you are loading will need to be identified. So the name of the program has to be known. So the header contains the name of the program, the starting address of the program, that means where it is going to be loaded in memory, and then the length of the whole program, and then the length of the whole program. So you should note that the header record will contain the name of the program, the starting address of the program, and then the length of the program, because this helps to determine how much memory your program is going to consume. Okay, so the operating system needs that information in order to load the program in memory. The name of the program, where it is going to begin from when loaded in memory, and then the length of the whole program, meaning how many bytes is it going to consume when fully loaded in memory. Okay, so that is the first record. Then we have other records which we call text records. Now the text records are the ones which consist of the instructions and the data which were generated when we were translating into machine language. So these are the instructions, the machine language instructions, plus the data of the program. Okay. Now it also contains where each instruction, that means where each instruction is going to be found in memory. That means it also consists of the address where these instructions are loaded. Okay. Then we have what we call the end record, which marks the end of the objective program. And then it also specifies the address where the program will begin executing from. So an objective program consists of those three important records. You remember, the header record has the name of the program, the starting address of the program, and then the length of the whole program. Then the text records, these are many, depending on how big your program is. They are the ones which show the translated machine language instructions. And then finally, the end record, which marks the end of the program. Okay. Now, the header record, it begins with the character H. Okay. Then it is followed by the name of the program. Okay. Then the starting address of the program, and then the length of the program in bytes. Okay. So it is one record. The first character is H, meaning header. Then the name of the program, it should be abbreviated so that it fits in only 6 characters. Okay. Then from the 8th character up to the 13th character, I think we have got 6 digits there. That is the starting address of the program. And then from 14 to 19, that is the length of the objective program. Okay. Someone is asking which chapter is this, guys? I don't know. What should we say? Sam, were you here in the previous program? In the previous lecture? Problem with you is that you want to read the notes as I teach, and then you don't listen. Then when you find the notes by yourselves, you will find a problem of understanding them. I prefer that you listen and we go through this. Then when the time comes for revising, then you can read. But when you read as I teach, I doubt whether you will pick much, because everything will look very okay. But when you are on your own, you will find a problem. So it is better that you listen and then we work out this thing together. When I tell you write, then you write. Okay? Now, let us generate the header record for this program which we have seen, the program which was translated into machine language. Okay, let us look at this header record first. Okay, do you see this screen here? Do you see our program here? Hello? Hello?
Yes, we can see. Yes, we can
okay,
see.
If you can see it, then let us write the header record. We said that the header record begins with the character H. Okay. Followed by the name of the program, which shouldn't exceed 6 characters. Okay, so can we write H? H, that is the first character, meaning.
Yes, sir, we are able to see it.
Okay, so I'm saying let us write the header record together. You write H. Okay, then that should be followed by the name of the program. Now we remember we said that the name of this program is called what? What is the name of this program? Nobody revised what we discussed last time, it seems. Anybody knowing the name of this program? I think I mentioned the name of the program. Okay, I said that the name of the program is usually, okay, the name of the program is copy. Very good. So we said that the name of the program is copy. So the header record begins with the H, followed by the name of the program, which is copy. Okay. Then it is followed by the beginning address. They are telling us that it is going to be written in using 6 digits. So you can see that this program is starting from an address 1000. So if we want to write it in 6 digits, then I think we should write 00 and then we write 1000. So we can put 2 zeros before the 1000 to make a 6 digits. Is that okay? Then that is followed by the length of the program, how big the program is. So to find how big the program is, it means that we have to calculate from the beginning address up to the last instruction of the program. Now the first instruction here, like we can see, begins from address 1000. So when we scroll down the program, I think you can see that the last instruction there is at address 2079. 2079, that's where the last instruction begins from. And it consumes 1 byte. I think you can see that directive output byte x05. So that is consuming only 1 byte. This byte is 05. You can see that it is only 1 byte. So if we begin that particular directive from 2079, it means it goes as far as which address? The last address will be, because the 2079 is the beginning of the last directive. So it means that the last one will be where? Can someone tell me the address, the last address? This one is consuming only 1 byte, and it begins from 2079. So it means that the other one, the last byte will be what?
Two zero seven.
To what?
207C.
This is 1 byte. This one is 1 byte. You can see it is 05. 05, those are 2 hexadecimal digits. Each hexadecimal digit is 4 bits. Now these ones are 2 bits, sorry, 2 digits, which means 8 bits, which means 1 byte. So it should be what? (207A). Very good, you are right. So it should be 207A. So we are beginning from 1000 up to 207A. So what is the length in between? So what is the length in between there? We begin from 1000 and we go up to 207A. So what is the length of the whole program? We are going as far as 207A, not 2079. (107A). That is very good. It is just subtracting. We said that the last directive of that program ends at 207A. So it is just a matter of subtracting 207A. You subtract 1000, which is the beginning, and then we will remain with 107A. But according to the instructions, the length of the program has to fit in 6 digits. Therefore, we write 00107A. So the header record begins with the H, followed by the name of the program, which is copy, followed by the beginning address of the program, which we said is written in 6 digits, which is 001,000, then followed by the length of the program, which is 001070A. Okay, so when we look at the header record, I think you can see the header record. Do you see the header record? H, followed by the name of the program copy, followed by the beginning address, then followed by the length of the whole program. Is that okay? Anybody having a question there? I don't want to leave anybody behind. We are trying to write the object program. So no problem. Can we continue? If you can't talk, or maybe you can write in the chat. If you want me to continue, then we continue. If you don't want me to continue, then you tell me why. So can we continue? Are you hearing me?
Yes, sir, we are hearing you. You can continue.
Okay. So because I want you to, if you don't want to answer, then you can just write in the chat. Because I don't want to continue when you are left behind. Okay, what is the meaning of that thing, the sign? It is just separating. It is just helping us to know the different fields that we need, but otherwise it is not needed. But if I ask you to write a program, maybe it is better that you put them there so that I can tell you what is what. Okay? It is just separating. It is just separating the different fields. First H, then the name of the program, then the beginning address of the program, then the what? Then the length of the whole program. So that is the header record. Now the object, the text records. Okay. Now the text records, we said that these are many depending on the size of the program. It can be one if the program is small, but they can be more than one in case the program is big. So a text record begins with the T, of course, meaning a text. That begins with the T. Okay, that is the first character. Then you write the beginning address of that record, the beginning address of that record. Okay. Then you write the length, how long that record is going to be in bytes. Okay. And then you write the object, the instructions. You write the machine language instructions. You remember we said that the text record consists of the what? The machine language instructions which were translated plus the address where those instructions are to be found. So we write just only the starting address, and then we specify how long the record is going to be, and then the object code. That means we write the instructions themselves in hexadecimal. Okay. Now, let us write the first text record again using our program. I want you to follow because this one is not a bit tricky, but you just need to be attentive. Okay. Otherwise, we are going to be, say, repeating it over and over again. So let us look at the program and then we write the text record. Okay. So we are saying that the text record is going to include the instructions which have been translated. That means we are going to write the machine language instructions which we see in the last column of the program. So the instructions, those are the ones we put. So you see that if there are many, then we need more text records. Now, according to the syntax of this according to the syntax of this text record, they are telling you that the instructions themselves, of course, are going to begin from the 10th character up to 69. 69 should be the maximum. It can be less, but don't write machine language instructions which are exceeding 69. So if we begin from column 10, and then we end at column 69, how many characters are we going to put in a record? What is the maximum number of characters in a record? If we begin from 10, and then we go up to 69, what is the maximum number of characters?
59.
We begin from 10, and we stop at 69. Both 10 and 69 are counted.
61.
62.
It is
61.
61.
Are you sure? Let us do something very small. Suppose I have 10 to 12, and I say I begin from 10, then 11, then 12. Each of these is counted. So how many do I have?
Like 3 characters.
Okay, so those are 3 characters. So if I begin from 10, so the last one is 12, and then I have 3 characters in between, not so? So here, if I begin from 10 and I stop at 69, how many characters do I have in between there?
60.
I think there are 60. Very good. Okay, so let us write the text record then. Let us write the text record of this program. So the first text record will begin with the T. Okay, that is 1 character, followed by the beginning address of that record. So here, I think this is the first instruction here, which we are going to translate. This one, which is 141033. So that one is found at the address 1000. Is that right? So that should be the beginning address of the first record. But they told us that it should be in 6 characters. So what do we write?
Can write the copy, then
text record. A text record begins with the character T, followed by the beginning address of that record, then followed by the length of that record, and then we write the machine language instructions, which shouldn't be more than 60 characters. So I am just wanting us to write the second field. The text record is beginning with the T. Then the beginning address is what? The first instruction is this one, 141033. At which address are we beginning from? That first instruction.
I think at address 1000, which when written in 6, we should have 00, then 1000.
Very good. So we write 00, 1000. Okay. Then they are saying that that should be followed by the length of the record. Now, The length, we can put that one later, I think, because we don't know where we are going to stop, okay? But when we start writing, they are telling us that we should not exceed 60 characters. So each of these instructions, I think, is 6 digits. And they are telling us that we shouldn't write more than 60. So where are we going to stop if we are going to write those instructions? Which would be the last instruction? These ones are very good. Each one is 6 digits. So what would be the last one? What will be the last instruction? Each of them is 6 digits. I think you can just do a simple calculation, because if each is 60, it means that how many of them are you going to put into the first record? No, it shouldn't be 4, 5, or 5, 4, 6. Each of these is 6 digits. Can't you see? 1, 4, 10, 33 is 6. 48, 20, 39 is 6. So we go on adding, and then we don't exceed 60. The last one should be 60. So which should be the last? I think it shouldn't be 4, 5, or 4, 4, 6. That one is very far. Okay, I think it should be that one, 0010 Eh? Is it clear to everybody? Because these are 6, 12, 18, 24, 30, 36, 42, 48, 54, then 60. It means this one is the last instruction. Is that right? So the last instruction in the first record will stop, will be 10-2D. So the first instruction is beginning, it is from 14, 10, 33. Then we write the next one, 48, 20, 39. Then the next is 0010, 36. All the way up to what? 0010 to D. Okay. Now we want to calculate the length of that record. Remember, we started from 1000. Now 0010 to D, here it starts from 101B. It starts from 101B, and it is 3 bytes, which means where does it stop? The last instruction. This address is the beginning address of the instruction, which is 0010 to D. It is beginning from 101B, and then it stops where? No, it doesn't stop there. It begins from, I am just wanting to tell me the last address. It begins from 101B, and it is 3 bytes. Each of these instructions, for the simple sake, you see we are lucky. They are all 3 bytes, so they don't give us a problem. They are all 3 bytes. So if it begins at 101B, then the last, it will be stopping where? 10(1)E, very good. So we are starting from 1,000 and we are stopping at 10(1)E. So what is the difference there? Because the difference will give us the size of the record, how many bytes that record is consuming. So what is the difference there? We started from 1,000 and we are going up to 1E, 10(1)E. So what is the length of that instruction? And they are saying we put it into 2 digits. Hello? If you begin from 1,000 and you stop at 10(1)E, what is the difference? Very good. So 1E is the length of the instruction. Therefore, the text record, the first text record, I don't know if you were writing, the first text record begins with the character T, followed by the beginning address. We have said it is 1,000, but we write that one using 6 digits. So we write 001,000, followed by the length of the record, which we have said is 1E. And then that is followed by the instructions, which we said we begin from 14, 10, 33, 48, 20, 39, and you go on writing until you stop at what? 0010(2D). Okay, so that is the first text record. So that is the first text record. Okay, so you can see the first text record here, which I have written in red. You begin with the T, followed by the beginning address, which is 001,000, followed by the length of the record, which we have calculated that it should be 1E. Then that is followed by the what? By the instructions themselves. We begin from 14, 10, 33, and we go on writing those instructions until 0010(2D). Is that okay? Is there any question?
Yes, sir. I just want to know how they got that 1E. Was it by subtracting or by adding? Because we started from 001,000 up to, is it 10(1)B there? How did we get the difference 1E?
I think I spent a lot of time on that. That is why I requested that we let us be very attentive. Otherwise, we are going to spend a lot of time. Okay, we said that first we concluded that 0010(2D) is going to be the last instruction in that record. Is that right? And we said the 10(1)B is where that last instruction begins from. And we said that if it begins from 10(1)B, then it will stop at where? At 10(1)E. So if we begin from 1,000 and then we stop at 10(1)E, we want to find the difference in between. We find the difference in between, and the difference is subtracting 10(1)E, you subtract 1,000, and I think you get 1E. Is that okay?
Yeah, it's clear now.
If someone is asking, why don't we put that one into 6 digits? The syntax of this Staff, they want us to put it into only 2 digits. They want us to put it into only 2 digits. So if you look, do you see my screen? They are saying the first character is T. Then you write the beginning address, which we have written that it should be 1000. And then the length of the object code in that record is 2 digits from 8 to 9. So it means we write only 2 digits. Okay. Then from 10 to 69, we calculated that the maximum should be 60 characters or 60 digits, which we are going to put there. So that's why we have that text record. Any other question? Okay, it is clear now. Very good. Can we write the next text record because the program is continuing? You remember we said that we can have as many text records as the program. If the program is big, we are going to load very many text records. If the program is small, then we will have fewer text records. So let us write the second text record. The second text record. So the second text record will also begin with a T. Are we together? So where are we starting from? Where are we starting from? This second record will start from which address? Very good. So it will start from 0010-1E because this 0C1036 is the first instruction in that record. And it is at 10-1E. So from T we write 0010-1E. Again, you can first leave the length because you don't know where we are stopping. Then according to this, I think the last information we need to enter is this word 0, because that is what we are entering last. The other information remaining is reserve word, reserve byte. Those are they are just telling us to reserve space. It is not any information which is going to be loaded in memory, but they are just asking us to reserve space for that. So we are stopping at this word 0, which is 000000. Now, if that word is beginning from 1030, where does it stop from? Where will it stop? It will stop at 1033. Okay, very good. So let us calculate the length in there. We started from 10-1E, and we are going as far as 1033. So what is the length of that record? If you begin from 10-1E and you stop at 1033, what is the length in there? It is 1 of 5. Very good. Therefore, then the second text record begins with the T, the beginning followed by the beginning address, which is 00101E, then followed by the length of the record, which is 15. And then we write the machine language instructions and the data, which we say begins from 0C1036. Then you continue 48, 2061, all the way up to what? 000000. Okay. This one doesn't exceed 60. It doesn't exceed 60, but that is where we stop the second text record. Okay. So you can see that the second text record. I have written the second text record here in blue, beginning with the T, followed by the beginning address of that record, followed by the length of that record, and then we write the machine language instructions up to 000000. Do you have any question about that?
Yeah, I have a question about the remaining instructions. I don't know whether the instructions or the directives, the reserve word, those ones. So is that to the processor or it's just to the programmer?
Okay, when you are writing, you remember we said that when you are declaring the variables, those directives, reserve word, reserve byte, and so on, we said they are usually at the bottom. Okay. Now, when you are entering information into memory, in memory, you load only data and the instructions. You don't load the empty space. We leave some empty space. We are just reserving that empty space, but it is not anything to be entered in memory. There is nothing we are entering in memory there. We are just reserving that space. Maybe we'll be putting there some information. I think when we copy, that is where we will be copying the information. But it is just reserving space. In the memory, we enter only instructions and the data. So you don't enter just, there is nothing to enter for reserve word and the reserve byte. Is it okay? Ladies and gentlemen, someone wants to know why we stopped at 10. Because that is where when you look at the program, we have space there. The remaining is just space. And we are not going to enter space. You don't enter just empty air. So that's why we are stopping. When you look at the program, okay, this last column, it is 0000 is the word, which is the last, as far as this particular program is concerned. It is the last there. Okay, so that is where we stop. The remaining is just the empty space. You don't enter anything. Empty space is not any, there is no information you are entering. Okay, so it is just reserving space. So are we telling the processor to do that? We are telling the assembler to do that, because you remember when you declare, it is like when you tell the compiler and you say int x, you are asking the compiler to reserve space for an integer, which you are going to put there sometime. Okay, And here, when I say reserve word, I am doing like the same thing. I am just reserving space. I'm not entering data yet there. No, this one is not the last text record. That is not the last text record because the program is continuing. The program is continuing, but we are stopping here because there is a lot of space which we are reserving. Empty space there. And we are not putting anything into that empty space. So that's why we stop that record there. When we find some other information to load, then we will begin from that address to load the other text records. Okay, the program does not stop there. Remember, there is a function, read the record, and there is also another function, write record. So the program is continuing. But when we find those instructions which are beginning like from read the record, then we will start entering that information. Okay. So you can see that we have more text records. We have more text records. Here we entered 2, but then when we go to function, read the record, you can see that we can then again begin from where that one starts. This one begins from write record. Write record, it begins from address 2039. That is where the first instruction is 041030. Okay. And then again, we will count 60 digits up to somewhere. So that will be the next text record. Okay. So I would request you during your free time to write the remaining text records for the whole program to make sure that you get those ones, that you get those answers that I put there. And remember, it is just by practicing. If you don't practice it, please don't expect to read these things in one night when you are going to do a test or an examination. You will not understand them. It is better you start reading them now. Okay. So I expect you to write the other text records. Now, finally, when you are done with the text records, we said that the last record is the end record. And they said the end record begins with the character E. And then you mention the address where the program is going to start executing. Because when you write the last instruction, then you mention you are ready to start executing. So you mention the address where you are going to start executing. Now, this one is going to start executing from the first instruction was at address 1000. Okay, so that is where we are going to begin from. So when we write the text record, when we write the last record there, it will begin with the E. The last record begins with the E, meaning end. And then we write the address where execution will begin from in memory. And we have said that it should begin from 1000 because that is the first instruction which we loaded in memory. Okay, so that is what you need to know about the object program. I want you to seriously revise it because we are going to be referring to the object program very often. So it is important that you know how to generate the header record, the text records, and then the end record. Before we continue, I want you to ask any question because this is very important. Okay, someone is saying it is okay. You have got the concept, then that makes me happy also. Okay, so I think we can continue now. Okay, usually sometimes when we are writing, some people prefer to put every record on just one line to make it look like a record. Okay, so this is what I did here, but it is not a must because when you are writing with a pen, you could find that you can't maybe put everything on one line. Okay, but some people prefer to have everything on one line. Every record, it will be consuming its own line. Okay. Now, machine-dependent features. Machine-dependent features. Now, remember, we have got two formats for the simple instruction computer. We have the simple SIC and then the SIC XE. So what we are trying to find out is how our instructions affected or which features will change when we change the machine. Because we saw, for example, when we were dealing with the simple SIC, you remember simple SIC, there is only one instruction format, which is opcode 8 bits, then bit number 9 to indicate the addressing mode, and then 15 bits for the address. So that is why we are seeing that for the instructions written using simple SIC, they are all 6 digits only, which means 24 bytes, which means 24 bits, which means 3 bytes. So that's why we are saying that every instruction is 3-3. So when we are writing here, I explained that the reason why here you have like intervals of 3 is that because every instruction is 3 bytes. So the space or the length from one instruction to another is 3. So that's why here the interval is always 3. For the simple SIC, we have got only one format, which is 3 bytes. But now if we change it to the XE, remember we have got 4 different formats. We don't have only one format, okay? Remember we have a format 1, which is only 1 byte. We have a format 2, which is 2 bytes. We have a format 3, which is 3 bytes. And then we have also format 4, which is 4 bytes. I hope you remember that stuff. So it means that if we are going to write the same program using the XE, now it is not always going to be 3 bytes, because all instructions are not the same length. Some are 1 byte, others 2, others 3, and others 4. Okay. Then you remember when we are also using the XE, we use like a format 2, we use registers, and we say the calculations where we are using registers. Calculations where we are using registers are better. They are faster. So if you have a chance of using registers, instead of going to memory now and again, You go to memory, you fetch the operands, you put them into a register, and then you work using registers. I think you saw those instructions which were modified, and then we use only the registers. Okay, so it means that the program can be modified, and then we can use the registers also, instead of having a program where you are going to memory now and again. And then the addressing modes are also going to change, because you remember for the simple SIC, how many addressing modes do we have for the simple SIC? How many addressing modes do we have for the simple SIC? Ladies and gentlemen, how many addressing modes do we have for the simple SIC, and what are they? Yeah, we have got only 2 addressing modes. What are they? What are those 2 addressing modes? I was asking before we were interrupted by the network that the addressing modes are also going to change. For the simple SIC, we have only 2 addressing modes. Very good. We have the index and the direct. But you remember when we came to the SIC XCE, we saw more addressing modes. Can someone tell me some addressing modes which we have found into the XCE? Any addressing mode which can be found into the XCE? Okay, very good. We have a program counter. We have a best relative. Okay, if I can remind you, we even have immediate addressing where we write using that hash. Okay, we have indirect addressing. Okay, so all of these ones are going to affect the instructions. So when we talk about machine dependent features, we are talking about those features which are affected when we change a program running on one machine and we take it to another machine. For example, now we are going to see the changes that are going to be found when we change from the XCE, from the simple SIC to the XCE. Now, this program that you see, it has been rewritten, the same program, but using some features of the XE, which we said are a bit superior. So like you can see, if you can look at this program here, we have things like a compare #0. Okay, we have such instructions, compare #0. But in the simple seek, every operand had to be a variable. Okay, we have things like LDA #3. Okay, so these are some features which are introduced when you are using a different machine. And then these features are going also to affect the machine language instructions. So things you should note is that we have got immediate operands. For immediate operands, we usually write a hash in front of the operand. Okay. Now, if you find an ampersand, like here, this instruction, which is at 002A, if you can pay attention, this one is saying jump, and then there is that ampersand sign, the each sign, return address. That sign indicates that the operand is going to be obtained using indirect addressing. So that ampersand there means indirect addressing. Okay. And where you find a plus in front of an instruction, that means that that is a format 4 instruction. You find that that one is a format 4 instruction. Okay. Now there are things I want you to note. Okay. For example, this plus here at 006, there is a plus on this instruction, jump to subroutine error direct. And we are saying that that is a format 4 instruction. A format 4 instruction is how many bytes? It is 4 bytes. Very good. Now, if it is 4 bytes, that's why you can see that it is a bit longer than the others. Yeah, so it has got 1, 2, 3, 4, 5, 6, 7, 8 digits. So if it has 8 digits and each digit is 4 bits, then it means those are 32 bits. 32 bits, those are 4 bytes. So that is why you see that if the instruction begins at 0006, then the next instruction will begin at 000A. It will not be 0009 because this one is 4 bytes. This one is a 4-byte instruction. So if it begins at 0006, then it should stop at 000A. Here it is not always 3 bytes. So it is the same thing here where you see a plus. You remember we said that wherever you find a plus, that is a format 4 instruction. So if it is a format 4 instruction, it is 4 bytes. That's why this particular one begins at 0013, and then it will end at 0017. Okay. The same thing applies here, that if it is at 0026 and it is a format 4 instruction, then it should end at the next instruction should begin at 002A. Okay. Now, when you see this is second program. The second program here is using some registers. We have instructions, for example, this one, compare registers AS. Yeah? Which format is that instruction, compare registers? Which format is it? Format 1, format 2, format 3, or format 4?
It's format 2.
Format?
2.
It is a format 2 instruction. Because the format 2 instruction, you remember we have the opcode and then it registers. Okay. How many bytes does it have? A format 2 instruction, how many bytes? It has 2 bytes. So that is why you see that if it begins from 49, okay, then the next one should begin at 10.4b. It is the same thing with these first instructions here, which are using registers. Here we are saying clear register X, clear register A, clear register S. Now, problem with those ones is that format 2 instructions, they usually talk about 2 registers. But then when you look at all of the 4 formats, at least it is only format 2 where you find the registers. So this one, instead of the second register, we put a 0. So it looks like we have got 2 registers. So if they are format 2 instructions, it means that each one is going to consume 2 bytes. So that when it begins with 1036, the next one begins at 1038, the next one begins at 103A. Is that right? Then the next one begins at 103C. But then this one, which begins at 103C, is 4 bytes. Okay? So there you add the 4. That's why the next one begins at 1040. Okay? So those things will change. So the instruction formats change, the addressing modes change when you are using the XE machine. And then the instructions also are going to be different. It is not just going to be a matter of using the opcode and the symbol table. No, because you know the format. Format 2 is registers, so you don't need an address. Format 3 is talking about a displacement. It is only format 4 which is talking about an address. Therefore, if we are going to translate these XE instructions, we are going to do some calculations. Okay, so you should be careful. So let us see what that means. What I have already explained, that the machine-dependent features, these are features which get affected when a program is running on different machines. So I'm sorry if my voice is breaking, but maybe it is because of the internet. Maybe it is because of the internet. Let me see. Okay, maybe it is better now. I hope it is better now. Okay, so what I am saying, we are reading here, where we are saying that what we mean by machine-dependent features, these are features which affect the machine language instructions when we change a machine from one machine to another. Okay, and then we are saying that that new program is running on the XE. That's why you see that so many things are changing. Okay. Indirect addressing, we have said that that is indicated by using an appendix hash, so that ampersand to the operand. Okay. Immediate operands, as usual, These are denoted by putting a prefix hash. Okay. Now, we have said that where possible, instructions which involve registers are preferred wherever possible. So wherever you have a chance of using registers, you use registers because registers are faster than going to memory. Remember, registers are found in the CPU itself. So if the operands are within the registers and the if the operands are in the registers and the registers are the CPU, then your operations are going to be fast because calculations are performed in the CPU. Okay. Now, for example, they are telling us how some instructions have changed. There was an instruction which was saying compare 0, and they're saying it has been replaced by compare registers A and S. I think they have put the 0 into register S so that now we say compare registers, compare the accumulator with what is in register S. This one, which was comparing 0, was comparing the accumulator with what is at memory location is 0, which we found is a 0. Okay? So you have to go to memory to find what is in memory location is 0, and then you compare it with what is in the CPU, the accumulator, which is in the CPU. But now you are comparing what is in the registers. If what is at memory location is 0 is put into register S, then you compare registers AS. There is another one which says TIX max len. That means increment register X by 1, and then compare the new value in register X with what is at memory location max len. Now here, what is at memory location max len, you can put it into register T, and then you set TIXR T. That means you are incrementing register X, and then you compare the new value of register X with what is in register T. I think you remember that, okay? So here, if you are going to translate these instructions into machine language, you just use the operation code table and then the codes of those registers. For example, if you are going to translate this instruction, which is compare registers AS, okay, that is a 2-byte instruction. So what you need is the opcode for compare register, okay? And then you get the code for register A and the code for register S. Does someone have that table to tell us the opcode for compare register? The opcode for compare register. Can someone find that one for us? The opcode for compare register. Is someone checking for us? Is there someone checking? Okay, very good. It is the S0. You remember the format?
It's A0.
Very good. Thank you. So you remember the format. If it is a format 2 instruction, you remember it is opcode, then R1, R2. Now, if the opcode here is the S0, then we put what is the code for the accumulator? Does anybody remember the code for the accumulator? It is a 0, so R1 is a 0. How about the code for register S? It is a 4. Very good. So that is why you see that this instruction here, which says compare registers AS, where is it? This instruction, you compare registers AS, it is the S004. The opcode is the S0, then the next 0 is register A, then the 4 is register S. So that one is very simple to translate. You just read the opcode, and then you put the codes for the registers, okay? We have this one here, which is TIXRT. We said that whenever you have registers, you use the format 2. But in case you have only one register, the second register, you make it a 0. The second register, you make it a 0. So like here we have TIXRT. What is the opcode for TIXR?
So it's B8.
It is B8, very good. And what is the code for register T?
It's 50.
It is what?
50.
It is 5, not 50. It is 5. Therefore, we remember we said that we need 2 registers for format 2. So the opcode is what? B8. Is that right? The first register is register T. Its code is 5, but we don't, because we don't have another register, we put here with 0. So that's why the machine language instruction is B850. Okay, are you following? Then we have these ones here, clear X. This is also format 2, like we said. The opcode of the instruction clear is B4. Then register X, its code is a 1. But because we have only one register, for the second register, we put a 0. So that instruction becomes B410. Then the next one is clear A. Again, the opcode for clear is B4. Register A is a 0. The second register is not there, we put a 0. Clear S, the opcode for the instruction clear is B4. Register S has got a code of 4, and we don't have a second register, we put a 0. So those ones are easy to translate. Okay, so those instructions are easy to translate, like you can see there. Okay, any question about that? Is it okay? How we translate like a format 2 instructions? Instruction is where the operands are registers. Anybody having a problem with that?
No, sir.
Okay. Now, how about these instructions where we have the operand in memory? We have these instructions where the operand is in memory, like this one, for example, STL return address. Okay. Now, you remember, if this one, if the operand is in memory, we use either format 3 or format 4. Format 3, we have got the opcode, then we have the flags. We have format 3, we have the opcode, then we have the flags, NIXBPE, and then we have a displacement. That is the format 3. Or we use the format 4, which also has the opcode, and then the flags NIXBPE, and then an address. So it is not like simple seek where we just have opcode and the address. Here we have to know what we are going to put into the flags, and then we are going either to calculate the displacement or to use an address. Okay. Now, how do we do this? How do we do this? Now, it is very simple. It is very simple, but you have to be attentive. All instructions where the operand is in memory, all instructions where the operand is in memory, we translate them using program counter or base. You remember, we have the flags for program counter and the base. So all instructions where the operand is in memory, that means where you have a variable, you translate them using program counter or base. Okay. Now, usually base address, usually program counter is preferred. In most cases, you use the program counter first. Okay. And when the program counter doesn't work, we will see cases where program counter doesn't work. That's when you go to base. That's when you consider base. Okay. Now, in the case base doesn't also work, then we go for format 4. Then that is when we go for format 4. But you should remember that usually for all instructions where you need to go to memory to get an operand, you use the program counter first, because we use the format 3 first. Okay. And within the format 3, we can Are you hearing me? now? Hello? Do you hear me now?
Yes, sir. Now we can hear you.
Okay. So I was saying that we have seen how to translate format 2 instructions. It is very easy, but for instructions where the operand is in memory, we first try format 3. We first try format 3. And when we try format 3, we use program counter first. When the program counter doesn't work, then we can try base. So if base doesn't also work, then we can go to format 4. Because the memory, it is either format 3 or format 4 if the operand is a memory location. Now let us look at this first instruction, which is STL return address. STL return address. STL return address. Okay. So here we are not just going to say opcode is 14, return address is here 0030, and then we say 140030. No, because we don't have that format for the SIG-XE. We don't have a format which just says the opcode address. But format 3, you remember it is opcode, bits NIXBPE, and then the displacement. Okay. Now, if we are going to use the program counter, like I have told you that for all instructions where the operand is in memory, you first try format 3. And then when you are in format 3, you try program counter first. Okay. So format 3, I hope everybody remembers, we begin with an opcode, which is 6 bits. Then we have flags N, I, X, B, P, E, and then we have a displacement. Do you remember that? Or maybe you can write that if you had forgotten. Format 3, you begin with an opcode, which is 6 bits. Then you have flags N, I, X, B, P, E, and then a displacement, which is 12 bits. Okay, you have written that?
Yes, sir.
Okay, then we are going to fill in these fields in order to get the machine language instruction. So you can begin with the, if you want, you can begin with the opcode first. Now the opcode for STL, I hope you remember we said it is 14. Do you remember that? Store what is in register L to return address. It is 14. Okay. Do you remember that?
Yes, sir.
Okay, now when we convert that to binary, I want you to be very careful here. 1 is 0001, and the 4 is what? 0100. Those are 8 bits. Okay? But the format takes only 6 bits. The format takes only 6 bits. So which means that we have to chop off some 2 bits. I want you to be careful, to listen carefully. The opcode, when you write it in binary, it takes 8 bits. But some formats, like a format 3 and a format 4, the opcode is required in only 6 bits. So which means that we have got some 2 bits which we are going to chop off these 8. Now the bits which are always chopped off are the last 2 on the right. They are the bits which you'll do what, which you usually chop off first. The last 2 bits. Okay. So it means that the opcode is going to be only 0001, then 01. Have you got that? Can you write that? The opcode is 6 bits.
Yes, sir.
It's going to be 001, then 01, because we need only 6 bits. Okay. So we are going to use the format 3. I think the next thing we can put here is the E. Remember, we said the bit E can be a 0 or a 1. When is it a 0 and when is it a 1?
It's a 0 when it's format 3, and it's a 1 when it's format 4.
Okay, so we have said that we are going to use the format 3. Therefore, that bit is a 0. You can write it there. Okay. Now, we said that we usually try a program counter first. Now we use the program counter or base in order to calculate the displacement. Okay. Now, this is how we calculate the displacement using a program counter. Does anybody remember the definition of a program counter? Does anybody remember the function of a program counter? You have forgotten these things because there is no test or what? Okay, very good. Program counter is always holding the address of the next instruction, which is going to be fetched from memory. Very, very good. Okay. Now, we are here. The instruction we are going to translate is this one, STL or return address. It is loaded from memory location 0000. Is that right? Now, if we are going to use the program counter is supposed to be holding the address of the next instruction. So what is the address of the next instruction? According to this program, what is the address of the next instruction? STL or return address is at address 000. The next instruction is at 0003. Okay, so the address of the next instruction is 0003. So when we are trying to translate this instruction, which is STL or return address, the program counter is already loaded with the value 003. Is that clear? When we are at this instruction, STL or return address, the value in the program counter is already 0003. Okay, so we calculate the displacement by getting the difference between the address of the operand and the value in the program counter. Can I repeat that? We calculate the displacement by getting the difference between the address of the operand and the value in the program counter. Okay. Now, what is the address of the operand? Return address. What is its address? Where is it found? At 0030, very, very good. Therefore, we get the difference between the address of the operand, which is 0030, and the value in the program counter, which is 003. So let us get that difference. (002D), very, very good. So the displacement is supposed to be 12 bits. Therefore, we can write only 02D because these are 4 bits, 4 bits. So the displacement is 02D. We can leave out 10 there. Okay. Then let us fill in the flags. Let us fill in the flags. P is a 1 because we have used the program counter. When you use the program counter, P is a 1. Are we together? Okay. Because we use the program counter, we did not use the base. So B is a 0. B is a 0. We didn't use the base. Okay. X is also 0 because we have not used the any indexing. There was no indexing. X is a 0. Okay. Then N and I, those are 1s. N is 1 and I is 1 because we are not using indirect or immediate addressing. Remember the bits. If I can remind you, N and I, if they are zeros, they can be 0, 0, 0, 1, 1, 0, 1, 1. We said that if N is 0 and I is 1, that means immediate. If you remember that. When N is 0 and I is 1, that is immediate. But like you can see, immediate operands, we usually put a hash. But this instruction, STL or return address, STL or return address, there is no hash. Therefore, it can't be 0, 1. Okay? It can't be indirect addressing because we said that with the indirect addressing, we have this ampersand sign in front of the operand. But here return address, we don't have anything. Therefore, it can't be 1, 0. Because 1, 0, any 1, I 0 means indirect addressing. And we have shown you how the indirect addressing is used. It can't also be 0, 0 because we said that when you use 0, 0, then the bits B, P, and E don't have meaning. They are just part of the displacement. But here they have meaning because we have already said that we need to have a P1 because we have used the program counter. We need to have a B0 because we have not used the base. We need the E0 because we are using format 3. Therefore, it can't be also B00. So the only alternative remaining is n has to be 1 and I is 1. Okay. So we have finished entering everything. The opcode, like we said, is 001, 0001, 01. Then we are saying n is 1, I is 1, x is 0, b is 0, p is 1, e is 0, and then the displacement is 0 to d. So when we convert these to hexadecimal, we have 0001, that is a 1. We have 0111, that is a 7. Then we have 0010, that is a 2. So our machine language instruction becomes 17202D. This is, I knew this would cause a problem because you people, you don't want to listen. We examined all the possibilities of n and I. If you can write those ones, n can be 0, I is 0. N can be 0, I 1. N can be 1, I is 0. And then they can also be 1 with both of them. So we started by eliminating 0, 1, because we said that when n is 0 and I is 1, that is immediate addressing. And we know how immediate addressing looks like. There is always a hash in front of the operand. But here you don't see a hash at return address. Therefore, we can't use 0, 1. Is that okay? Then we have 1, 0. If n is 1 and I is 0, we said that that is indirect addressing. And according to what I have just explained, if it is indirect addressing, they will put that ampersand, the each sign in front of the operand. Now, when you look at the instruction we are talking about, STL or return address, it does not have that ampersand. Therefore, it can't be 1, 0. So even 1, 0 is eliminated. So we are remaining with only either 0, 0 or a 1, 1. Now we said that when you use 0, 0, then the bits B, P, E do not have their usual meaning, and they are just appended to the displacement. But here our bits B, P, E, they have a meaning because, for example, we have assembled using a program counter. We need to indicate it that P is a 1 because we have calculated the displacement using program counter. We have also assembled using format 3. Therefore, E has to be a 0. Okay? Even B has to be a 0 because we have not used the base. So those ones, they have to be used. So if 0, 0, if you use 0, 0, it means these bits don't have meaning. But in our case, they do. Therefore, we are not going to use 0, 0. So the only alternative remaining is 1, 1. Is it clear now?
So even our x, it's going to be a 0.
Even an x, we said it is a 0 because we have not used the index addressing. We have not used any x anywhere. So x is also a 0. So when you put those bits, opcode is 0001, 0, 1. N is a 1, I is a 1, X is a 0, B is a 0, P is a 1, E is a 0, and then the displacement is 0 to D. When you convert this to hexadecimal, then you get 1720.D as the machine language instruction. Is that clear?
Yes, sir.
Okay. Can I beg that we continue from there next time? Because
Yes, sir.
these things involve calculating and our time has expired. So let us stop there and then we'll start with another instruction, with another example. But I request you to revise these things, ladies and gentlemen. They are not hard, but they need the constant revision. So if you are a person who usually convinces himself that you will read when a test is announced, I'm afraid you will get a problem. Okay, so you better start today. Okay, have a nice day, a nice evening, and I think a nice weekend.